Here's what they don't tell you about Mars. The most important thing we've found, there isn't a selfie, a dust devil, or a weird rock that looks like a face. It's chemistry. Quiet, stubborn chemistry locked inside ancient lake mud and river delta stones. Chemistry that might point to something living long ago. If that sounds like hype, good. Because by the end of this video, you'll know exactly what was found, why it matters, and what still stands between us and the truth about life on Mars. Before we get into the details, picture this in your mind. A basin shaped like a wide bowl, a river that once ran into it, carrying silt and clay, fanning out into a delta. Not on Earth, on Mars. Not last week, billions of years ago. That basin is called Jezero Crater, and it's where NASA landed the Perseverance rover. Jezero wasn't picked for a pretty view. It was picked because deltas are natural time capsules. On Earth, deltas trap organic bits, tiny minerals, and signs of life in layer upon layer of mud and sand. If Mars ever had life, even simple microbes, a delta is where its story would most likely be saved. Perseverance didn't go alone. It carries a pocket lab on wheels. There's a laser that can sniff rocks from a distance. There's a camera that can zoom and see grain textures close up. There's a tool that shines ultraviolet light to map certain molecules. There's an X-ray instrument that can tell what a rock is made of down to tiny spots. There's even a radar to peek under the surface. And then there's the part that might end up in the history books. A drill that pulls out small cores, seals them in ultra-clean tubes, and stores them for a future mission to bring back to Earth. So, what's the problem we're trying to solve here? It's simple to say, but hard to prove. We want to know if Mars ever hosted life. Not green aliens. Not even worms. We're talking about microbes, the kind you'd need a microscope to see. On Earth, microbes leave behind clues. Certain minerals that form in water, certain shapes in rocks, certain layered textures, and most important, certain organic molecules. But many of these clues can also form without life. So the challenge is to separate the "life did this" signals from the "geology did this" signals. That's the heart of the Mars mystery. Perseverance started by driving across a floor that turned out to be more complicated than expected. Some of the first rocks were igneous, formed from magma or lava, rich in olivine, and altered by water later. That alone is useful, because igneous rocks can be dated precisely when you bring them to a lab. The timeline matters. If you date an igneous rock, and then a sedimentary rock that formed in a lake on top of it, you can bracket when the lake existed. You can say, this lake was here after X and before Y. That's how you build a clock on a planet with no people and no written records. Then Perseverance reached the feature that had everyone excited, the delta. This is where ancient river channels split and dropped their load, as the flow slowed down coarse stuff first, finer mud later. In deltas, you can get sandstone, siltstone, and mudstone. Mudstone is the golden ticket if you're hunting for organic molecules and tiny bits of chemistry that can preserve through time. The rover measured these rocks with its instruments and started drilling cores. Here's where it gets interesting. The rover's instrument that uses ultraviolet light can excite certain molecules and make them glow in ways that show their structure. When it scanned some delta rocks, especially fine-grained, layered ones, it found signs of organics. Not plastics, not something from the rover, but carbon-based molecules built in a way we often see in natural settings. Are they proof of life? No. Could they be made by non-living chemistry? Yes. But their presence in the right rocks, in a place that was once a lake, is exactly the kind of signal you would expect if there were once living things, or at least the right conditions for them. Alongside the organics, the rover found minerals that tell a clear story about water, clay minerals, sulfates, carbonates, hematite. On Earth, clays often form when water lingers and alters volcanic ash or basalt. Sulfates can show up when water evaporates and concentrates salts. Carbonates can form in water that holds dissolved carbon dioxide. Hematite can form in water or by oxidation processes. Put these together and you get a picture. Long-lasting water, changing chemistry over time, and conditions that could have supported microbes that like chemical gradients, places where energy is stored in the mix of minerals and fluids. Think about that for a second. If you were going to design an outdoor lab for microbes, little cells that eat iron, breathe sulfate, or use simple organic molecules, you would give them water, rock surfaces filled with reactions, and a stable environment. Ancient Jezero delivered that. Calm lakes can settle fine sediments that bury and protect fragile molecules from radiation. River deltas bring in fresh nutrients. Layers build up. Time does the rest. Now, a quick pause to clear up a common confusion. The rover found organic molecules. That is not the same as finding fossils. Organic, in chemistry, just means carbon-based. You can make plenty of organic molecules without life. Meteorites can carry them. Chemical reactions on rock surfaces can build them. Sunlight, carbon dioxide, water, and minerals can do a surprising amount all by themselves. So we have to be careful. What makes the finding strong is not just that organics were seen, but where and how they were seen. Inside sedimentary rocks, linked with minerals formed in water, and sometimes concentrated in specific layers. On Earth, that pattern often points to life, or at least to environments where life likes to grow. If you've heard about methane on Mars, you might wonder how that fits in. Over the years, other missions reported small amounts of methane in the air at certain times and places. Methane can come from geology, like water reacting with certain rocks, or from living microbes. The methane story on Mars is still messy. Some instruments detect it, others don't. It varies with seasons or local conditions. Perseverance's job isn't to solve methane from the air, its job is to read the rocks. But if Mars once had methane being made in the ground, that would create another chemical food source for microbes, just like we see in some places on Earth. Let's return to the delta. The rover team targeted specific rock units that looked like fine lake mud turned to stone. In some of these, the instruments picked up signals of aromatic organics, ring-shaped molecules, and other complex carbon compounds. The X-ray tool mapped elements like carbon, sulfur, phosphorus, and nitrogen at small scales. These are the building blocks of life. Finding them together doesn't prove life, but it means the pantry was stocked. You also get structures in the rocks, laminations, tiny crossbeds that form as mud settles and currents shift. On Earth, microbes can make layers more sticky or trap fine grains, but purely physical processes can do that too. So again, we collect clues, but we don't jump to conclusions. Another key part of this story is the way rocks record pH and redox conditions. Basically, how acidic the water was and how oxidizing the environment was. Many Mars rocks show signs of water that was neither too acidic nor too basic, and with changing redox conditions that could power microbial metabolisms. Think of iron. If some iron is reduced and some is oxidized, microbes can tap that gradient. If you have sulfate and sulfide, microbes can do the same. The minerals in Jezero tell us those gradients existed. The chemistry of the organics suggests they were not all zapped away by oxidants or radiation. That's a good sign for preservation. Here's something else that matters: timing. The age of the delta is thought to be around 3.5 to 3.8 billion years. On Earth, that window overlaps with the period when life either arose or was already around in some form. We don't have a perfect record from Earth because plate tectonics and weather have recycled many of our oldest rocks. Mars kept more of its early crust. If life ever started on both worlds, it may have done so under similar early solar system conditions: warming from the young sun, frequent impacts, lots of volcanic activity, and water moving through rocks. Jezero's rocks could hold a cleaner record of that era than most rocks on Earth. Now, let's talk about one of the most important ideas in this entire mission: biosignatures. A biosignature is a signal that life, and only life, can realistically make. That could be a certain balance of isotopes, like a preference for lighter carbon atoms in organics, which some microbes on Earth show. It could be specific molecules that are very unlikely to form without biology. It could be textures that match microbial mats, or stromatolite-like forms. It could be microfossils, tiny cells preserved in minerals. Here's the catch: most of the strong biosignatures require lab-level tools to confirm. The rover can hint, it can point, it can map. But the final call probably needs a microscope, a clean lab, a mass spectrometer the size of a room, and scientists who can test and retest. That's why the sample tubes matter. When Perseverance drills, it takes a pencil-thick core, slides it into a tube, and seals it. Each tube is as clean as we can make it. The rover stores these and places some in safe spots on the ground as backups. The plan is to bring them home. Once on Earth, we can slice a rock thinner than a hair to see tiny layers. We can heat it in a vacuum to sniff released gases. We can measure isotopes precise to parts per thousand. We can look for patterns that don't match random chemistry. That's how we turn maybe into yes or no. But until those samples arrive, we still have plenty to learn from the rover itself. Take the way organics were found. They weren't smeared everywhere. They showed up more strongly in certain layers, often the fine, dark ones. That's what you'd expect if organics were trapped in quiet water or concentrated in certain beds. The rover also found carbonates in some rocks. On Earth, carbonates can trap and preserve microfossils and organic matter. Even if no fossils are there, carbonates record the chemistry of the water they formed in. That can tell us about the climate and the carbon cycle of ancient Mars. Let's talk climate. For a lake to sit in a crater, you need water flowing in and not freezing solid right away. Early Mars probably had a thicker atmosphere, more greenhouse gases, and active volcanism that released water vapor and carbon dioxide. The delta shows that the water wasn't just a flash flood. It lasted long enough to build layers. We see crossbeds, we see different grain sizes, we see signs that the river changed over time. All of that points to a climate that allowed liquid water to exist, at least sometimes, on the surface. That matters for life, because life needs time. A quick splash won't cut it. Now, a word on contamination. You might ask, how do we know these organics aren't from the rover? NASA took a lot of care to keep the rover and tubes clean. The instruments can spot common contaminants. They also compare signals inside the rock to signals on the surface. If organics are inside mineral grains or trapped in tiny pores that formed long ago, that's not from a wheel rolling by. Plus, the rover sees patterns that match geological layering. Contamination wouldn't do that. Is this perfect? No. Nothing in field science is perfect, but the chain of evidence is strong enough to take seriously. We should also talk about how rocks change after they form. Mars is cold and dry now, but it still has brines, salty water that can move through the ground and alter minerals. Some organics can be changed by radiation near the surface. Oxidants in the soil can break them down. So, if we're still finding them in certain layers, that means those layers protected them. Fine grains help with that. So do certain minerals like clays, which can shield organics from damage. The fact that organics show up in these protective settings is another encouraging sign. Another piece of the puzzle comes from the grains themselves. When you zoom in, you can see if grains are sharp or rounded, if they're sorted by size, and if they show ripples. This tells you about the water's speed and depth. Calm lake beds lay down thin laminae of fine mud. Faster channels drop sand. If organics are more common in thin, fine layers, that fits the idea of quiet water where organics could settle out. If you had a strong, turbulent flow, organics would be more likely to break down or be flushed away. Let's shift to energy sources. Life needs energy. On Earth, sunlight is a big one, but underground life often uses chemicals: iron, sulfur, hydrogen, methane. The minerals found in Jezero hint that early Mars had these chemical energy sources. For example, if water flowed through olivine-rich rocks, it could produce hydrogen gas. Microbes on Earth use hydrogen. If you have iron that can switch between oxidation states, microbes can tap that too. If you have sulfate minerals, microbes can use them the way we use oxygen. None of this proves life, but it says the menu was there. Now, where are we in the story? We have a lake. We have a delta. We have rocks laid down by water. We have minerals that form in water. We have organics inside some of those rocks. We have a clock that places all this near the time when life on Earth was getting started. We have a plan to bring samples home. What we don't have yet is a smoking gun, a microfossil with clear cell walls, a set of isotopes that screams biology, a pattern of molecules that chemistry alone almost never produces. That gap is why people say, no, this is not proof of life, and they are right to say it. But it's also why these findings are exciting. They point us to the right rocks, the right layers, the right questions. Let's zoom in on one more angle: why sedimentary rocks are so powerful for this hunt. Sedimentary rocks are built from pieces of older rocks, minerals, and organic matter that are moved by wind or water and then compacted. The fine grains in mudstones settle slowly in calm water, trapping whatever is in the water with them: salts, organics, tiny mineral crystals. Over time, minerals can grow in the spaces between grains and lock everything in place. On Earth, that's how we preserve leaves, shells, and even soft tissues in rare cases. On Mars, we're not expecting leaves, but the same lock-in process can preserve chemical traces. The fact that Perseverance found organics mainly in these fine, layered rocks is exactly what you'd hope for if you wrote the search plan from scratch. It's also worth looking at the bigger picture of Mars. We now have multiple lines of evidence that long ago the planet had rivers, lakes, possibly even a northern ocean. Deltas show up in a number of craters. Minerals linked to water are widespread. Volcanoes were active. The atmosphere was thicker. The magnetic field was fading, which matters for radiation levels. As Mars cooled and dried, surface water disappeared, but underground pockets may have stayed wet for longer. If life ever started, it could have retreated into the subsurface. Perseverance is exploring an ancient surface lakebed. One day, a future mission might drill deeper. For now, deltas are our best chance at finding preserved signs from the surface world. You might hear people say, "We've found organics on Mars before. What's new?" Yes, older missions detected organics too, but Perseverance's findings stand out because of the rock types, the context, the spatial mapping, and the plan to return samples. Think of it like this: finding gasoline smell in the air near a road is one thing. Finding a fuel stain in a parked car's tank is another. Context tightens the story. The rover's instruments can map where the signals are strongest and how they line up with layers. That context is gold for the lab work we will do on Earth. Let's also clear up what possible biosignatures means when teams use that phrase. It doesn't mean we saw tiny fossils. It usually means we saw a pattern that might be made by life, but that can also be made by non-life. And we need more data. That might sound cautious to the point of boring, but it's how science protects itself from wishful thinking. We've had false alarms before. Meteorites with shapes that looked like microfossils, later debated. Methane spikes, later questioned. The point is not to avoid excitement. It's to build a case that stands up when everyone tries to knock it down. Okay, so let's imagine the best case future. The samples come back. In a clean lab, scientists slice into a mudstone from the delta. Under a powerful microscope, they see layered textures with tiny repeating forms tied to old biofilms. Chemical tests show organic molecules with structures that are much more common in biological systems. Isotope measurements show a preference for lighter carbon that matches known biological fractionation. Minerals around these zones show they formed at low temperatures in water. The date lines up with the right era. When you stack all that, the conclusion would be hard to avoid. Mars once had life. Even if the life was simple, that would change how we see ourselves and our place in the universe. Now imagine a different, but still important outcome. The samples come back and show complex organics that formed without life, through long chemical pathways powered by water, rock, and time. That would still be huge. It would prove that prebiotic chemistry can go pretty far on a dry, cold world. It would tell us that building blocks are not rare, that chemistry pushes toward complexity whenever it can. That would feed into the search for life on icy moons like Europa and Enceladus, and on exoplanets. There's also a third outcome. The samples come back and show that organics existed, but they're too altered to say if they were ever biological. That would be frustrating, but it would also refine our map. It would tell us which environments on Mars are good at preserving biosignatures and which are not. Science is a long game. Even a not sure is a step forward when it points the next rover to a better spot. Let's circle back to the rover itself for a moment, because Perseverance is more than a rock collector. It tested making oxygen from the Martian air, which is mostly carbon dioxide. That matters for future crews. It carried a small helicopter that scouted ahead and proved powered flight in thin air. It studies weather and dust that affect how long gear can survive. But for our story today, the star is still those cores sealed in metal tubes. That's the bridge between a desert of questions and a lab full of answers. There's one more layer to all of this, the larger story about life beyond Earth. We've found thousands of planets around other stars. Some are rocky, some are in the just right zone for liquid water, some may have thick atmospheres. We can't go there yet, but Mars is next door. If we prove life existed on Mars, even once, it tells us that life might be common. If we don't, it doesn't mean life is rare. It just means conditions and timing matter, and Mars missed a key step, or lost it later. Either way, Mars is our first real test of the idea that life springs up when given a chance. You might be thinking, this is all great, but how sure can we be right now? Here's the honest answer. We are sure about the water story. Deltas, lakes, long-lasting wet conditions. We are sure that the rocks in Jezero hold minerals that form in water. We are sure that organics are present in some of those rocks. We are not sure what made those organics. We are not sure whether any are biological. We are not sure whether clear biosignatures are preserved. That's why the sample return is the key. The rover has set the stage. The lab lights are warming up. The question is waiting. Now, let's bring this home by walking through one sample's journey. The rover spots a fine-layered rock in the delta. The cameras show tight laminations. The laser reads its chemistry from a distance and notes interesting signals. The UV mapping tool scans a patch and sees organic signatures linked to certain minerals. The X-ray instrument measures elements that matter for life chemistry. The team picks a spot, drills, and pulls out a core. The core shows visible layering. It goes into a tube, which is sealed. The tube is logged and stored. Later, the rover drops a cache of tubes in a spot where future landers can reach them. Down the road, a lander arrives. A small rocket launches the cache into orbit, and an orbiter carries it home. In a lab, people who have trained for years open that tube in a clean room. They test tiny slices in multiple ways. They argue, they check, they repeat. That's how you turn a desert pebble into a yes or a no for one of the biggest questions we can ask. All of this leads to a simple thought. We went to Mars to look for life, and the planet answered with a whisper instead of a shout. It gave us old lake beds, gentle mud layers, and molecules hiding in stone. It didn't give us a fossilized fish or a leaf print. It asked us to be patient, to build tools, to collect, to bring back, to think. It pushed us to accept that big answers often start as small signals. That's not a letdown. That's how real discovery works. There's also a human side. Think of the people who built the rover, tested it, and then watched it touch down in a place that had been a dot on a map for decades. Think of the teams who name rocks based on themes so they can talk about them quickly. Think of the long drives, the dust on the wheels, the moments when a drill bit jams and everyone holds their breath. Science is a story about planets, but it's also a story about people trying again and again until the data are clear. If you've stayed this far, here's your takeaway in plain words. Mars once had a lake and a river delta at Jezero. Perseverance found minerals that form in water and carbon-based molecules inside the right kinds of rocks. Those molecules could be made with or without life. The rocks look like the kind that, on Earth, are good at preserving signs of life. The rover packed samples that can be tested back on Earth with tools strong enough to tell us what's real. We are closer to the answer than we have ever been, but we're not at the finish line yet. So, what should you watch for next? Watch for news about which samples are most promising. Watch for updates on the plan to get them back. Watch for new findings as the rover explores different layers of the delta, including places where the water was deeper or the chemistry was different. Each new core adds a page to the story. Each new scan draws the map a little sharper. And if you like the bigger question, are we alone? Remember this. Finding life on Mars doesn't just change Mars. It changes the way we look at Earth. It tells us that life might be written into the rules of chemistry. It tells us that the universe might be full of places where chemistry tips into biology, given time, and water, and rock. Or, if we don't find life there, it tells us that life is a delicate event that needs a rare mix, and that Earth is even more special than we thought. Either way, we win knowledge. Let me leave you with a simple image. A core of dark, fine-grained rock from an ancient Martian lake sits in a silver tube. wrapped in labels and numbers, quiet as a secret. Inside that core are atoms, arranged in patterns made by water, time, and maybe, just maybe, cells that lived and died before any animal ever walked on Earth. That tube is small. The question it holds is not,